Take a deep breath and let your body settle into the soft embrace of your surroundings, allowing the tension of the day to dissolve like mist in the morning sun. As you release your final exhale, find a place of stillness, where the only movement is the slow, rhythmic rise and fall of your chest. There is a profound, heavy comfort in the warmth of a summer evening, a sensation governed by the intricate laws of physics and the patient tilt of our planet. As the sun begins its slow descent toward the horizon, we enter the period often called the golden hour, but from a meteorological perspective, this is a transformation of light and energy. During this time, the sun's rays must travel through a much thicker layer of the Earth's atmosphere, up to 10 to 12 times more air than when the sun is directly overhead at noon. This journey causes a phenomenon known as Rayleigh scattering. Because the shorter wavelengths of light, like blue and violet, are scattered away by the nitrogen and oxygen molecules in the air, only the longer wavelengths, the deep reds, oranges, and golds reach your eyes. This isn't just a visual change, it is the physical filtration of the spectrum, wrapping the world in a low-energy, warm-toned glow that registers at a color temperature of approximately 2000 to 3000 Kelvin, a stark contrast to the 5600 Kelvin of midday light. As you sit or lie there, perhaps you can imagine the feel of a stone wall or a paved path that has been baked by the sun all day. Even as the air begins to still, these surfaces remain intensely warm to the touch. This is due to a property called thermal mass. Materials like concrete, brick, and stone have a high volumetric heat capacity, meaning they act like thermal batteries. On a typical 90-degree summer day, asphalt can absorb enough solar radiation to reach surface temperatures of over 140 degrees Fahrenheit. As the sun sets, these surfaces don't cool instantly. Instead, they begin a process called long-wave radiation. They slowly release that stored energy back into the air, immediately surrounding them. If you were to walk past a brick building at dusk, you would feel a wall of heat radiating outward, not from the sun, but from the building itself, finally exhaling the warmth it gathered since dawn. This evening warmth is further sustained by the invisible weight of humidity. You might notice the air feels thicker or more velvety as the light fades. This is the interplay between temperature and the dew point. The dew point is the atmospheric temperature below which water droplets begin to condense. In the height of summer, if the dew point is above 65 or 70 degrees Fahrenheit, the air is saturated with water vapor. Interestingly, water vapor is actually less dense than dry air. Nitrogen and oxygen molecules are heavier than H2O molecules, but moist air traps heat with incredible efficiency. This is because water has a high specific heat capacity. It requires a significant amount of energy loss for the temperature to drop. Consequently, a humid evening acts like a soft, invisible blanket, preventing the rapid escape of heat into the upper atmosphere and keeping the night air balmy and close. Listen closely to the evening air, and you might hear the rhythmic, pulsing chorus of crickets. This sound is more than just a summer soundtrack. It is a living thermometer. In 1897, a scientist named Amos Dolbear published a paper noting the relationship between the chirping rate of the snowy tree cricket and the ambient air temperature. This is now known as Dolbear's law. You can actually calculate the temperature in Fahrenheit by counting the number of chirps you hear in 15 seconds and adding 40 to that number. Because crickets are ectothermic, or cold-blooded, their chemical reactions, and thus their muscle movements, speed up as the air warms and slow down as it cools. The very tempo of the evening is dictated by the kinetic energy of the molecules in the air. As you visualize this summer landscape, notice the sky opposite the setting sun. In the east, a dark blue-grey band begins to rise from the horizon. This is not just a cloud, it is the shadow of the Earth itself being cast upward into the atmosphere. Above this shadow, you may see a pinkish-orange glow known as the belt of Venus. This occurs because the setting sun's light is being backscattered by the atmosphere. While the ground beneath you remains warm, the atmosphere above is beginning to layer itself. This leads to a fascinating acoustic phenomenon called a temperature inversion. During the day, air is usually warmer near the ground and cooler higher up, which causes sound waves to bend upward and dissipate. But in the evening, as the ground begins to cool, while the air a few hundred feet up remains warm, sound waves are refracted, or bent, back down toward the earth. This is why, on a still summer evening, you can hear the distant chime of a bell, the low hum of a far-off train, or the laughter of neighbors 3 blocks away with startling clarity. The physics of the evening air literally carries the world's whispers to your ears. The air around you also carries the scent of the evening, a fragrance that feels green and heavy. This is partly due to the shutdown of photosynthesis. As light levels drop below a certain threshold, plants stop consuming carbon dioxide and begin a period of respiration. Many plants also release organic compounds called terpenes, essential oils that become more volatile in the heat. When the air is still and humid, these molecules hang low to the ground rather than being carried away by midday thermals. If there was a light afternoon rain, you might also smell petrichor. This scent is caused by a soil-dwelling bacteria called actinomycetes, which produces a compound called geosmin. When raindrops hit the warm earth, they trap tiny air bubbles that then burst out of the droplet, like natural aerosols, carrying the scent of the earth upward for you to breathe in. In the gardens and meadows, another transition is occurring. Fireflies or lampyridae begin their rhythmic display. This light is a marvel of biological engineering, a process called bioluminescence. Inside the firefly's abdomen, a chemical called luciferin combines with oxygen in the presence of an enzyme called luciferase. This reaction is nearly 100% efficient, meaning almost no energy is lost as heat. It is cold light. The frequency of their flashes is often dictated by the temperature of the evening, much like the cricket's chirp. In the stillness of a 75-degree evening, the air is literally pulsing with chemical signals, a silent conversation happening in the cooling air. If you are in a city, you may experience the urban heat island effect. Because urban areas are composed of vast stretches of dark, non-reflective surfaces like asphalt and roofing, they absorb significantly more solar radiation than rural areas. A city can remain 1 to 7 degrees Fahrenheit warmer than its surrounding countryside well into the late evening. This is compounded by waste heat from air conditioners and engines. However, as you settle into your space, imagine a gentle breeze beginning to stir. This is often an anabatic or katabatic wind, a thermal transition where cooler, denser air from shaded areas or higher elevations begins to flow downward to replace the rising warm air of the lowlands. It is a natural respiration of the landscape, a soft, cooling touch against the lingering warmth of the day. The textures of a summer evening are distinct. The air feels tactile, almost like a liquid, as the relative humidity rises. Relative humidity is a measure of how much water vapor is in the air, compared to the maximum amount the air could hold at that specific temperature. As the temperature drops in the evening, the air's capacity to hold water decreases, causing the relative humidity to climb even if no new moisture is added. This is why your skin might feel slightly damp, or why the grass begins to feel cool and slick with dew. The dew forms because the grass blades lose heat through radiation faster than the air does, reaching the dew point temperature and causing water vapor to condense directly onto the surface. As the last remnants of the sun's light, those crepuscular rays that fan out like a golden crown, finally disappear, the world doesn't turn cold. It remains held in a state of thermal equilibrium. The trees, the soil, and the very walls around you are all participants in a grand exchange of energy. A single mature oak tree can lose up to 100 gallons of water a day through a process called evapotranspiration. This process actually cools the air immediately around the tree, creating pockets of refreshing coolness amidst the summer heat. As you breathe in, imagine that cool, oxygen-rich air being shared by the forest, moving in slow, invisible currents through the night. The science of this moment is one of balance. The Earth is radiating its daily intake of solar energy back out toward the stars, a process that has occurred for billions of years. This long-wave infrared radiation is the Earth's way of breathing out. While the sun's shortwave radiation brought the heat of the day, this evening transition is the cooling response, a slow, measured return to a state of rest. Even the speed of sound changes slightly. In the warm 80-degree air of a summer dusk, sound travels at about 1,139 feet per second, slightly faster than it does in the cold of winter. Everything about the world right now, the sound, the scent, the temperature and the light is tuned to a specific, high-energy frequency that is only just beginning to mellow. Feel the weight of your limbs as you consider the immense scale of this seasonal rhythm. The warmth you feel is the result of the Earth's 23.5-degree axial tilt, which allows your hemisphere to lean toward the sun, soaking up photons that traveled 93 million miles just to warm the ground beneath your feet. That energy is still here, lingering in the wood of your bed frame, the bricks of your home, and the very marrow of your bones. It is a physical reminder of the sun's abundance, a lingering hug from the day that is now passing into history. As the atmosphere continues to settle, the turbulent winds of the afternoon give way to a laminar flow, where the air moves in smooth, parallel layers. This stillness is not just a feeling, it is a fluid, dynamic reality. The world is becoming quiet, the energy is shifting from kinetic to potential, and the stage is being set for a deep, restorative rest. You are a part of this cycle, a living being tuned to the thermal pulse of the planet. Let the lingering warmth of the summer evening cradle you, knowing that the science of the world is working in perfect harmony to bring you to this moment of absolute, warm, and sun-drenched peace. What's happening now is a subtle shift in the physics of your environment, a transition that our ancestors observed with a mix of reverence and scientific curiosity long before the invention of the modern barometer. Consider the way the air feels against your skin at this very moment. It possesses a lingering, heavy quality that doesn't simply vanish when the sun dips below the horizon. This persistence of warmth is a result of seasonal lag, a meteorological phenomenon where the peak temperatures of summer occur several weeks after the summer solstice. Although the Northern Hemisphere receives its maximum solar radiation around June 21st, the warmest evenings typically arrive in late July or August. This occurs because the Earth's massive oceans and land masses act like a giant thermal flywheel, requiring a tremendous amount of energy, specifically 4,184 joules per kilogram for every degree Celsius in the case of water to raise their temperature. We are living in the release of that stored energy, the planet's long, slow exhale of heat that has been accumulating for months. History tells us that ancient civilizations were deeply attuned to this specific atmospheric weight. The Romans referred to the most stifling part of the summer as the dies caniculares, or the dog days. They observed that during this period, Sirius, the dog star and the brightest star in the constellation Canis Major, would rise and set with the sun. From a modern astronomical perspective, we know this is called the heliacal rising. While the Romans incorrectly believed that the combined light of Sirius and the sun created the oppressive evening heat, their observations correctly identified the peak of the seasonal thermal cycle. At this point in the year, the atmosphere has expanded significantly. Warm air is less dense than cold air, and as it heats up, the molecules move more vigorously, pushing outward and causing the entire column of air above you to take up more physical space. Picture the world as a cooling hearth, where the fire has been extinguished, but the stones remain too hot to touch. This is a perfect analogy for thermal inertia. Scientists discovered that different materials on Earth have vastly different rates of thermal conductivity. Dry air is a remarkably poor conductor, with a thermal conductivity of only about 0.026 watts per meter Kelvin. This means that the heat trapped near the surface doesn't easily escape into the upper atmosphere. Instead, it remains hugged close to the ground, creating that cozy, envelope-like sensation you feel on a porch or near a garden wall at twilight. In the late 18th century, pioneering meteorologists like Luke Howard, the man who first classified clouds into categories like cirrus, stratos, and cumulus in 1802, began to realize that the city itself was a source of heat. He noticed that London evenings were consistently warmer than the surrounding countryside, a discovery that laid the groundwork for our modern understanding of the urban heat island effect and how human-made structures alter the local microclimate. Notice how the light changes as we move deeper into what is known as civil twilight. This is the period when the sun is between 0 and 6 degrees below the horizon. During these minutes, the atmosphere acts as a massive lens. Because the air is denser near the surface, it bends or refracts the sunlight around the curvature of the Earth, allowing us to see light even after the sun has physically disappeared from view. In high-latitude regions like Scandinavia or northern Canada, this transition stretches into the white nights, where the sun never sinks far enough below the horizon for true darkness to take hold. In these parts of the world, the evening warmth is a precious, fleeting guest. In the Mediterranean, however, the evening brings a different phenomenon, the Meltemi, or Etesian winds. These are dry, cool winds that blow from the north across the Aegean Sea, caused by the pressure gradient between the Siberian high and the Asian low. They provide a predictable, rhythmic cooling that has dictated the architecture and sailing schedules of the region for over 3,000 years. At this very moment, the plants in your vicinity are undergoing a process called stomatal closure. During the peak heat of the day, plants open tiny pores on their leaves called stomata to take in carbon dioxide for photosynthesis, but they also lose water through transpiration in the process. To conserve moisture in the intense heat of a summer evening, many plants close these pores. This reduction in transpiration means that the biological cooling system of the local vegetation slows down, contributing to the perceived stillness and warmth of the garden. Scientists have measured that a single acre of corn can transpire up to 4,000 gallons of water a day, acting as a massive, natural evaporative cooler. When that process pauses at dusk, the local humidity often spikes, as the moisture released during the day remains suspended in the cooling air. Consider the wet bulb temperature, a measurement that reflects how effectively an object can cool itself through evaporation. On a dry summer evening, your body can cool itself efficiently. However, when the dew point, the temperature at which the air becomes 100% saturated with moisture, reaches 70 degrees Fahrenheit or higher, the air can no longer easily accept more water vapor. This is why some evenings feel close or heavy. The physics of evaporation dictates that it takes 2,260 kilojoules of energy to turn 1 kilogram of liquid water into vapor. When the air is already saturated, that energy stays on your skin as heat rather than being carried away. Humans have historically managed this by building wind towers, or malkafs, in ancient Persia and Egypt, architectural features designed to catch the high-altitude breezes and funnel them down into living spaces, using the principles of pressure differentials to create natural air conditioning. Within the soil beneath you, a different kind of heat exchange is occurring. Ground temperatures at a depth of just 6 inches can lag behind the air temperature by several hours. While the air begins to cool at 8 p.m., the soil may still be reaching its peak temperature from the 2 p.m. sun. This ground heat flux is the reason why many burrowing animals, like toads or certain insects, emerge only late in the evening. They are waiting for the air to match the temperature of their subterranean homes. This thermal synchronization is a fundamental beat in the world's internal clock. What's occurring now in the upper atmosphere is the formation of the nocturnal boundary layer. As the ground cools, a stable layer of air forms near the surface, effectively capping the atmosphere and preventing the turbulent mixing of air that happens during the day. This is why the wind often dies down at sunset. The atmosphere becomes stratified or layered like a cake. This stability allows for the concentration of scents and sounds. History tells us that early sailors used these evening conditions to navigate by the smell of the land, as the evening breeze is now moving from the cooling land toward the still warm sea in a land breeze cycle carried the fragrance of pine, earth, and blooming jasmine miles out into the ocean. Deep within the molecules of the air, the Stefan-Boltzmann law is at work. This law states that the total energy radiated per unit surface area of a black body is proportional to the fourth power of its thermodynamic temperature. In simpler terms, the warmer the Earth's surface, the more intensely it radiates infrared energy back into space. On a clear summer evening, this radiation is your primary source of cooling. If there were a layer of clouds, they would act as a thermal mirror, reflecting that long-wave radiation back to the ground. But on a clear night, the energy escapes toward the stars at the speed of light. You are witnessing a planetary cooling system that has functioned with mechanical precision for billions of years, a constant balancing of the Earth's energy budget. Consider the global perspective of the monsoon evening in Southeast Asia. While we associate summer with dryness, for billions of people, summer evenings are defined by the latent heat of condensation. As massive clouds form and rain begins to fall, the phase change from water vapor to liquid releases an enormous amount of heat back into the atmosphere. This is why a tropical rainstorm can often leave the air feeling warmer and more humid than before the clouds arrived. It is a reminder that weather is not just a local event, but a global redistribution of energy, moving heat from the equator toward the poles in a constant, churning cycle of convection. Notice the blue hour, or l'heure bleue, a term coined by the French to describe the specific period of twilight when the sun is far enough below the horizon that the sky takes on a deep, saturated indigo hue. This isn't just an aesthetic choice by nature, it's a result of Chapuis's absorption. While Rayleigh scattering makes the sunset red, the ozone layer in the upper atmosphere absorbs specific wavelengths of light, allowing only the deep blue light to pass through when the sun is at a particular angle. Scientists have found that this specific blue light has a distinct effect on the circadian rhythms of both humans and animals, signaling the brain to begin the production of melatonin, the hormone responsible for sleep. Even the color of the sky is a biological instruction, a quiet command for the world to begin its descent into rest. As we dwell in this historical and scientific understanding of the evening, we find a sense of timelessness. The same physics that governed the cooling of a Roman villa or an Egyptian courtyard is currently operating in the room around you. The absolute humidity, the actual mass of water vapor in a given volume of air, might be high, but as the temperature subsides, the relative humidity climbs, reaching toward the saturation point. This is a moment of profound equilibrium. The frantic, high-energy state of the afternoon is being replaced by the steady, low-frequency vibration of the night. Every stone, every leaf, and every molecule of air is participating in this inevitable transition, moving from the excitement of the sun toward the stillness of the stars. You are part of this grand, predictable rhythm, a witness to the Earth's eternal capacity to gather heat and then, with a gentle, atmospheric sigh, let it all go. Imagine the atmosphere right now as a grand, planetary slow cooker. Just as a heavy ceramic pot retains heat long after the stove has been clicked into the off position, the Earth continues to simmer in the energy it collected during the peak daylight hours. This is due to a concept known as sensible heat, which is the energy we can actually feel as a change in temperature. In contrast, latent heat is the energy tucked away within the water vapor, hanging in the air. On a muggy July evening, you are experiencing the synergy of both. What's happening now is that the ground is attempting to shed this energy, but the humid air acts like a heavy velvet curtain draped over the landscape, preventing that heat from escaping into the cold vacuum of space. Consider the porch or the window where you are mentally perched. If you were to press your palm against a wooden railing and then against a stone step, you would feel a distinct difference in their thermal personality. Wood has a low thermal conductivity, roughly 0.12 watts per meter Kelvin, meaning it doesn't transfer heat very quickly. It feels warm, but not intensely so. Stone, however, has a conductivity nearly 20 times higher, between 2 and 3 watts per meter Kelvin. This makes the stone feel like a solid block of captured sunlight. This difference in how materials hold and release energy is why a forest feels cool and breathable, while a brick courtyard feels like a warm embrace well past midnight. Scientists use isotherms lines on a weather map that connect points of equal temperature to visualize these heat islands and cool pockets. At this hour, the isotherms are curving and shifting as the land begins its slow, uneven cooling process. What we often think of as a simple, hot day is actually governed by massive, invisible structures in the sky. Picture a giant, rotating dome of air sitting over the Atlantic Ocean. Meteorologists call this the Bermuda High. This is a semi-permanent high-pressure cell, or anticyclone, that dictates the summer weather for much of North America and Europe. In an anticyclone, air is slowly sinking from the upper atmosphere toward the ground. As it sinks, it undergoes adiabatic compression. Just like a bicycle pump gets hot as you compress the air inside it to fill a tire, the air in a high-pressure system warms up as it is pushed downward. This compression prevents clouds from forming and traps the day's heat near the surface. This is why summer evenings can feel so incredibly still. The high pressure is literally pinning the weather in place, creating a stable, warm bubble for us to inhabit. Deep within the sky, as the sun reaches an angle of about 4 degrees below the horizon, you might witness a compelling optical event if the air is clear enough. This is the green flash, a brief, vivid spark of emerald light on the upper rim of the sun as it disappears. This happens because the atmosphere acts like a prism, separating the sunlight into its component colors. The reds and oranges are the first to disappear, and for a fraction of a second, the green light is refracted most strongly toward your eyes. It requires a specific set of atmospheric conditions, a high-pressure system, and a clear path over the water to be visible. It is a reminder that the air is not just empty space, but a complex, fluid lens that is constantly bending and shaping the light that reaches us. At this very moment, the global movement of heat is unfolding on a staggering scale. In the Mediterranean, the evening might be influenced by the sirocco, a wind that originates in the Sahara Desert. These winds can reach speeds of up to 100 kilometers per hour, carrying dust and extreme heat across the sea. In Egypt, a similar wind called the Khamsin brings a dry, oppressive heat that can raise temperatures by 20 degrees Celsius in a matter of hours. These are examples of advection, where heat isn't just generated locally by the sun, but is physically transported across continents by the wind. Think of it like a giant hairdryer blowing across a room. Even if the room is shaded, the air remains hot because of the energy being pushed in from elsewhere. Notice how the air feels on your skin, which has its own thermal properties. The human body has a specific heat capacity of about 3.5 kilojoules per kilogram per degree Celsius. This means we are relatively resistant to sudden temperature changes, but we are very sensitive to the heat index. This index was developed in 1979 by Robert G. Stedman to describe how hot the air actually feels to a human being. It takes into account both the air temperature and the relative humidity. When the temperature is 90 degrees Fahrenheit and the humidity is 70%, the air feels like 105 degrees to our bodies. This is because the vapor pressure of water at 25 degrees Celsius is approximately 3.17 kilopascals. When the air is already crowded with water molecules, our own natural cooling through perspiration becomes less effective. The air isn't just hot, it is full, and our bodies must work in harmony with the environment to find a state of equilibrium. Picture the sky once more, not as a void, but as a container filled with microscopic particles called Aitken nuclei. These are tiny aerosols, ranging from 0.01 to 0.1 micrometers in size, consisting of sea salt, dust, or organic compounds. As the sun sets, these particles scatter the remaining light, creating the hazy, dreamlike quality of a summer dusk. The way these particles interact with light is a process called me-scattering. Unlike the Rayleigh scattering that makes the sky blue, me-scattering occurs when the particles are roughly the same size as the wavelength of the light. This produces the white or greyish haze often seen near the horizon on warm, humid evenings. It is as if the air itself has been infused with a fine, golden powder, catching the last of the day's energy and holding it for us to see. In the gardens, the chlorophyll within the leaves, a complex molecule with the formula C55H72O5N4Mg, is slowing its frantic activity. Chlorophyll activity generally peaks when temperatures are between 25 and 30 degrees Celsius. As the evening progresses and the temperature dips slightly below this range, the plant's metabolic rate shifts. This is similar to a factory slowing down its assembly line for the night. The energy production of the day is being stored as starches and sugars, a biological banking of the sun's wealth. As this happens, the ground heat flux continues to move energy upward. Scientists have measured that during the day, the ground absorbs about 1,361 watts per square meter of solar radiation, a value known as the solar constant, at the top of the atmosphere, though much less reaches the ground. In the evening, the ground returns this energy in the form of infrared radiation, which we experience as that comforting, rising warmth from the Earth. The physics of your immediate environment is also being affected by the Earth's position in its orbit. Interestingly, The Earth reaches aphelion, its farthest point from the Sun, at about 152 million kilometers in early July. You might expect this to be the coldest time of year, but because of the 23.5 degree tilt of the Earth's axis, the northern hemisphere is tilted most directly toward the Sun, overshadowing the effect of the distance. This tilt means the Sun's rays hit the ground at a more vertical angle, concentrating the energy. Imagine holding a flashlight directly above a table versus at a sharp angle. The direct light is much more intense. This concentrated energy is what creates the deep, penetrating warmth of a summer evening, a heat that feels as though it is soaked into the very core of the world. As the light fades, the radiation inversion begins to take shape. During the day, the sun warms the ground, which in turn warms the air. But at night, the ground cools much faster than the air above it. This creates a lid of warmer air sitting on top of a cooler layer near the surface. This inversion can be just a few hundred feet thick, but it has a profound effect on the atmosphere. It traps smells, sounds, and moisture. If you've ever noticed the scent of a distant barbecue or the perfume of night-blooming jasmine hanging perfectly still in the air, you are sensing the effects of this atmospheric lid. The world becomes a series of quiet, fragrant chambers, each one holding its own secret pocket of the day's warmth. Even the pressure of the air is in a state of rhythmic flux. There is a diurnal pressure variation, a twice-daily rise and fall of atmospheric pressure that usually amounts to about 3 millibars. Like a slow, deep breath, the atmosphere expands and contracts as it is heated and cooled. This subtle change in pressure is why some people feel more relaxed or even a bit drowsy as evening sets in. The weight of the world is literally changing, shifting its burden as the sun's influence wanes. Within this cooling landscape, the albedo of your surroundings plays a final role in the evening's temperature. Albedo is the measure of how much light a surface reflects. A dark asphalt roof has a very low albedo, between 0.05 and 0.15, meaning it absorbs up to 95% of the solar energy that hits it. A light-colored house, or a sandy path, might have an albedo of 0.4, reflecting much more of the heat away. In the evening, the dark surfaces act like thermal reservoirs, pulsing with the infrared light they gathered. You can almost feel the sensible heat vibrating off these dark objects, a tactile ghost of the afternoon sun. Invite your focus now to the sheer scale of the troposphere, the lowest layer of the atmosphere where all our weather occurs. It is only about 8 to 15 kilometers thick, a thin, delicate skin on the surface of the planet. Within this thin layer, all the complexities of the summer evening are contained. The Bermuda high, the radiation inversions, the latent heat of the humidity, and the slow cooling of the soil. As you rest, you are nestled at the very bottom of this ocean of air, protected by its weight and warmed by its memory of the sun. The atmosphere is not just a scientific concept. It is a living, breathing envelope that sustains the rhythm of your life. The warmth you feel is a physical connection to the celestial mechanics of our solar system, a lingering gift from a star 93 million miles away, curated and held close by the very air you breathe. At this very moment, your own biology is performing a sophisticated thermal dance with the summer air, a process that links your internal rhythm to the cooling curve of the planet. Scientists discovered that the human body operates on a circadian clock that is inextricably tied to core body temperature. For you to enter a state of deep restoration, your internal temperature must drop by approximately 1 to 2 degrees Celsius, or about 2 to 3 degrees Fahrenheit. This physiological downshift usually begins in the early evening, synchronized with the fading of the sun's shortwave radiation. As the air around you remains balmy, your body works to shed its metabolic heat into the environment. This is why a summer evening feels so personal. You are physically interacting with the climate, searching for that thermal neutral zone, which for a resting adult is typically between 25 and 30 degrees Celsius, or 77 to 86 degrees Fahrenheit. Consider the air in the room around you as a living extension of the landscape. Even if you are indoors, the mean radiant temperature of your walls is likely higher than the air temperature itself. This is because the materials of your home, the gypsum in the drywall, the timber in the frame, the glass in the windows, possess their own specific heat capacities. Wood, for instance, has a specific heat of about 1.7 kilojoules per kilogram Kelvin. Throughout the day, these materials have been absorbing thermal energy. Now, in the evening, they are releasing it through a process of convection and radiation. You are literally being held in a cocoon of stored daylight, a gentle secondary warming that persists long after the sky has darkened. In the 1970s, a researcher named P.O. Fanger developed the comfort equation, which identifies 6 primary factors that determine how you feel in this moment: air temperature, radiant temperature, air velocity, humidity, clothing insulation, and your own metabolic rate. On a still summer night, these variables align to create a sense of profound, heavy tranquility. Notice how the sounds of the world have shifted since the sun crossed the horizon. Deep within the trees and the grass, the insects have changed their tune. While the midday was dominated by the buzzing of bees and the high-pitched drone of cicadas, the evening belongs to the Sphingidae, or hawk moths. These remarkable creatures are the marathon runners of the insect world. Unlike most insects that rely entirely on the environment for warmth, hawk moths can vibrate their wing muscles to raise their internal temperature to as high as 45 degrees Celsius or 113 degrees Fahrenheit, allowing them to remain active in the slightly cooler evening air. They are drawn to night-blooming flowers like the evening primrose or the moonflower, which use the thermal stability of the dusk to release their potent fragrances. These plants have evolved a vespertine blooming cycle, opening their petals only when the sun's intensity has waned and the air is saturated with moisture, which helps carry their scent molecules further through the dense, stable air. Picture the atmosphere as a vast, slow-moving reservoir of thermal memory. In the 18th century, Daniel Gabriel Fahrenheit perfected the mercury in glass thermometer, giving us the first reliable tool to measure this memory with precision. He set his 0 point using a stabilized brine solution, but it is the evening temperatures that tell the true story of a season's character. On a global scale, we see this reflected in the way different cultures embrace the evening warmth. In Spain and Italy, the passeggiata, or evening stroll, is a cultural staple born of necessity. When the indoor air is trapped by stone walls that have reached thermal equilibrium with the midday sun, the outdoors becomes the only place to find a cooling breeze. This movement of people is a direct response to thermal inertia, the resistance of a physical object to a change in its temperature. What's happening now in the sky above is a phenomenon known as net radiation. This is the balance between the incoming solar radiation and the outgoing terrestrial radiation. During a summer evening, the net radiation becomes negative, meaning the Earth is losing more energy than it is receiving. This energy is escaping in the form of long-wave infrared radiation, primarily in a specific band of the electromagnetic spectrum called the atmospheric window, which sits between 8 and 13 micrometers. It is through this invisible window that the heat of the day leaks out into the cold of space. If you were to look at the world through an infrared camera right now, you would see the trees, the pavement, and even the air itself glowing with this escaping energy, a silent, luminous departure of the day's intensity. Scientists discovered that trees play an even more vital role in these evening transitions than we once thought. Through a process called hydraulic lift, some deep-rooted trees pull water from the moist subsoil during the night and release a portion of it into the drier upper soil layers. This not only sustains the forest but also contributes to a localized cooling effect. A single large oak tree can provide a cooling effect equivalent to 10 room-sized air conditioners operating for 20 hours a day. As you breathe in the evening air, you are inhaling the cool, moist exhale of the vegetation around you. This is the big picture of summer, a massive, interconnected system of biological and meteorological heat exchanges designed to maintain the delicate balance of life. At this very moment, permit your awareness to settle on the concept of sensible heat flux. This is the process by which the warm ground transfers its energy to the air directly above it through conduction. Because air is a poor conductor, this heat transfer is slow and methodical. It creates a microclimate just a few inches above the soil that is significantly warmer than the air at eye level. If you've ever noticed your pet seeking out a specific patch of carpet or a certain corner of the garden in the evening, they are often responding to these subtle thermal gradients that we, as humans, usually overlook. Our experience of the evening is a composite of these tiny, localized events, woven together into a single, cohesive sensation of warmth. Consider the historical perspective of how we have lived within these summer rhythms. Before the advent of modern HVAC systems, humans utilized evaporative cooling in ingenious ways. In ancient India, people hung koos mats, woven from fragrant vetiver grass over their doorways, and kept them damp. As the warm evening air passed through the wet fibers, it triggered a phase change in the water molecules. Turning liquid water into vapor requires a significant amount of energy, approximately 2,260 joules per gram. This energy is taken from the air itself, dropping the temperature by as much as 10 or 15 degrees. This is the same principle that keeps you comfortable when a light breeze hits your skin on a humid night. The air is physically carrying away your body's heat through the energy-intensive process of evaporation. Notice how the dew point depression, the difference between the actual air temperature and the dew point, is narrowing. As the temperature falls toward the dew point, the relative humidity rises. When the two numbers meet, the air is 100% saturated, and dew begins to form. This is the saturation point. For many, a dew point of 60 degrees Fahrenheit is considered comfortable, while a dew point above 70 degrees feels tropical. This measurement is a much more accurate reflection of how a summer evening feels than the temperature alone, as it dictates the vapor pressure deficit. A low deficit means the air is nearly full of moisture, creating that signature, velvet-thick atmosphere that makes the summer evening feel so intimate and enclosed. Deep within the Earth's oceans, a similar but much more massive process is unfolding. Water has a thermal capacity about 4 times greater than that of air. This means the oceans are the great stabilizers of our planet's temperature. A summer evening near the coast is moderated by the marine layer, a mass of cool, dense air pushed inland by the temperature difference between the water and the land. This is a density current, a fundamental principle of fluid dynamics where cooler, heavier air slides under warmer, lighter air. Even if you are hundreds of miles from the sea, the air you breathe is part of this global circulation, a vast network of currents and eddies that distribute the sun's warmth from the equator to the poles. Observe as your body recognizes the thermal comfort of this moment. This isn't just a feeling, it is a state of mind that occurs when your heat loss is in perfect equilibrium with your heat production. In this state, your heart rate often slows slightly, and your peripheral blood vessels dilate, a process called vasodilation, to bring warm blood closer to the surface of your skin. This is your body's way of opening its own internal windows to the evening air. It is a biological signal of safety and abundance. Throughout history, the summer evening has been a time of community and rest because it represents the peak of the Earth's productivity, a time when the growing degree days, a measure of heat accumulation used by farmers to predict plant development, are at their highest. The bigger picture of this warmth is its role in the phenology of our world, the study of periodic plant and animal life cycle events. The timing of the first firefly, the ripening of a tomato, and the song of the cricket are all dictated by the accumulation of thermal energy. We are part of this chronological record. As you rest in the warmth, you're experiencing the culmination of months of solar investment. This isn't just one night. It is a link in a chain of events that stretches back to the spring thaw and forward to the autumn harvest. The atmosphere is a grand archive, and the warmth of this evening is the latest entry, a heavy, golden chapter written in the language of thermodynamics and light. Allow the weight of this knowledge to settle over you like a soft quilt, knowing that you are exactly where you belong in the grand scientific order of the seasons. A closer look reveals that as we transition from civil twilight into nautical twilight, the period when the sun sits between 6 and 12 degrees below the horizon, the very chemistry of the air changes. At this moment, the atmosphere is no longer being bombarded by high-energy ultraviolet radiation. Instead, it is bathed in a soft, scattered light that triggers a fascinating shift in our own biology known as the Purkinje effect. This occurs because the human eye possesses 2 types of photoreceptors: cones for color in bright light and rods for grayscale in low light. As the evening warmth persists, your rods begin to take over, making reds and yellows seem darker, while blues and greens appear more vivid. This is why the deep indigo of a summer sky feels so much more intense than the blue of a midday sun. Your eyes are literally retuning themselves to the lower energy of the evening spectrum. Observe the way sounds carry through the heavy, warm air of a summer night. There is a physical reason why a distant voice or the chirp of a cricket seems to resonate more clearly now. Because the air is warmer, the molecules possess more kinetic energy and are vibrating more rapidly. The speed of sound is directly proportional to the square root of the absolute temperature. At a balmy 30 degrees Celsius, or 86 degrees Fahrenheit, sound travels at approximately 349 meters per second, or 1,145 feet per second. This is significantly faster than it does in the cold of winter. Imagine the evening atmosphere as the wooden body of a cello. The high-tension energy of the day has been the bow across the strings, and now the air itself is vibrating with the resonant frequency of that stored energy, carrying the world's melodies with a rich, liquid clarity. The scents that define a summer evening are also a matter of precise chemistry. As the soil temperature remains high, around 75 or 80 degrees Fahrenheit, it continues to release volatile organic compounds, or VOCs. If there was a brief shower earlier, the smell of petrichor becomes dominant. This scent is primarily caused by geosmin, a chemical byproduct of soil-dwelling bacteria. Human beings are incredibly sensitive to geosmin. We can detect it at concentrations as low as 5 parts per trillion. To put that in perspective, that is the equivalent of a single teaspoon of liquid in 200 Olympic-sized swimming pools. The warmth of the evening air acts as a carrier, increasing the vapor pressure of these molecules and allowing them to float more freely toward your senses. This isn't just a pleasant smell, it is a direct chemical communication from the earth to your olfactory system. Deep within the canopy of the trees, the katydids have begun their mechanical rhythm. While crickets use their legs, katydids, specifically the Pterophylla camellifolia, produce sound by rubbing their front wings together, a process called stridulation. Each wing has a scraper and a file made of a tough protein called chitin. The frequency of their song is entirely dependent on the ambient temperature. In the warmth of a 75-degree evening, they might pulse their wings at a rate of 50 to 60 times per minute. As the night eventually cools, this rate will drop with mathematical precision. This is because their metabolic enzymes, like all chemical catalysts, are temperature sensitive. The soundscape you hear is a living, breathing graph of the evening's thermal energy. Consider the mixing ratio of the air around you, the mass of water vapor compared to the mass of dry air. On a humid summer evening, the mixing ratio might be as high as 15 to 20 grams of water per kilogram of air. This moisture is a powerful greenhouse gas on a microscale. It absorbs the long-wave infrared radiation being emitted by your body and the ground, reflecting some of it back. This is why a clear, dry desert evening cools off so rapidly, dropping perhaps 40 degrees in a few hours, while a humid evening in the south or the tropics remains stagnant and warm. The water molecules are like tiny, transparent mirrors, keeping the day's heat locked in place. What's happening now in the plant world is a shift toward nighttime transpiration. While it was once thought that plants completely shut down their water use at night, scientists discovered that many species continue to lose between 5% and 15% of their daily water supply through their leaves, even after sunset. This process is driven by the vapor pressure deficit, the difference between the moisture inside the leaf and the moisture in the warm evening air. As the plants breathe, they release oxygen and a cocktail of terpenes, which are organic hydrocarbons. These terpenes can actually help seed the formation of tiny clouds or mist by acting as cloud condensation nuclei. The very fragrance of the pine or the lavender in your garden is a functional part of the local weather system. Notice the soil's thermal diffusivity, a measure of how quickly heat moves through a material. In a garden with sandy soil, the heat from the day penetrates quickly but also leaves quickly. However, in clay-rich soil, the heat is held with more tenacity. This evening, the clay is acting as a massive thermal battery, slowly conducting heat back up toward the surface at a rate of about 1 to 2 centimeters per hour. This means that at 10 p.m., the heat you feel underfoot may have originated from the sun's position at 2 p.m. This slow, upward migration of energy ensures that the roots of the plants stay warm, encouraging the growth of thermophilic or heat-loving bacteria that nourish the ecosystem. On a global scale, these summer evenings are shaped by massive wind systems like the Mistral in southern France or the Bora in the Adriatic. The Mistral is a cold, dry wind that accelerates through the Rhone Valley, often reaching speeds of 90 kilometers per hour. While it brings a chill, its arrival on a summer evening is often welcomed because it clears the atmosphere of aerosols, leading to sunsets of unbelievable clarity and a sudden drop in humidity. In contrast, the Mediterranean thermal low can create a vacuum effect, drawing in warm, moist air from the sea and keeping coastal evenings balmy and thick. Each of these winds is a response to the temperature differences between the land and the water, a planetary effort to reach a state of equilibrium. Scientists discovered that the human skin has an emissivity of approximately 0.98, which is nearly that of a perfect black body. This means our skin is exceptionally efficient at radiating heat away in the form of infrared energy. As you sit in the warmth of the evening, your body is constantly scanning the environment. If the surrounding walls and air are close to 30 degrees Celsius, your body struggles to shed its internal 3-7 degree Celsius heat. This leads to a state of relaxation where your blood pressure may slightly drop as your heart doesn't have to work as hard to maintain your core temperature against a cold environment. You are, in a very real sense, at home in the warmth. Picture the sky once more and notice if you see any high-altitude clouds that look like small, turreted castles. These are altocumulus castellanus. Their presence on a summer evening is a sign of elevated instability. It means that while the air at the ground is stable and calm, several thousand feet up, the air is churning and rising. However, if the evening remains clear, it is likely due to a capping inversion, a layer of warm air that acts like a lid, preventing any of that rising air from turning into a storm. This invisible cap is what preserves the peace of your evening, keeping the energy bottled up in a gentle, non-destructive form. Deep within the flora, the night-blooming cereus, a member of the Cactaceae family, may be preparing to open. These rare flowers are programmed by the circadian oscillation of their internal proteins. They wait for the specific light level of nautical twilight and a drop in the intensity of solar radiation to unfurl their petals. They are pollinated by bats and large moths that navigate using the Earth's magnetic field and the faint light of the stars. This biological event is perfectly synchronized with the physical cooling of the atmosphere. The flower's scent is most potent when the humidity is rising, ensuring its signal carries through the dense evening air. Consider the summer triangle, the prominent asterism formed by the stars Vega, Deneb, and Altair, which begins to appear overhead as the twilight deepens. These stars are massive, burning suns located light years away, yet their light is reaching you through the same atmosphere that is currently holding onto the day's heat. Vega, the brightest of the three, has an apparent magnitude of 0.03, making it one of the first points of light to pierce through the blue hour haze. The presence of these stars is a reminder of the Earth's orientation in the Milky Way. We are currently facing the dense center of our galaxy, and the warmth of our summer is a local symptom of our planet's tilt toward our own sun. What's occurring now is a total atmospheric harmony. The soil is conducting, the air is convecting, and the planet is radiating. The latent heat of vaporization that was stored in the humidity during the afternoon is now a reservoir of potential energy, keeping the evening air soft and forgiving. You are living inside a massive thermodynamic engine that is slowly, gracefully winding down for the night. The sensory experience, the smell of the earth, the sound of the katydids, the indigo hue of the sky is the visible and audible evidence of these physical laws in action. Every molecule is obeying the laws of entropy, moving from a state of high-energy chaos toward a state of quiet, warm order. You are a witness to this elegant transition, held safely in the grip of a season that knows exactly how to transition from the fire of the day to the velvet of the night. As the sun moves beyond 18 degrees below the horizon, we transition from nautical twilight into astronomical twilight. This is the moment when the last vestiges of scattered solar light vanish from the atmosphere, and the sky achieves its true deep space darkness. What's happening now is a complete shift in the Earth's energy budget. During the day, the planet was in a state of absorption, but now it has fully entered a phase of radiative cooling. Because the atmosphere is transparent to certain wavelengths of long-wave infrared radiation, specifically in the range of 8 to 14 micrometers, the heat that was gathered by the soil, the trees, and the pavement begins its final ascent. This energy doesn't just dissipate, it moves in a step-by-step journey from the solid Earth through the layers of the troposphere and out into the vast cold sink of the universe, which sits at a temperature of just 2.7 Kelvin. Notice the sensation of the air in your room as this cooling process reaches your window. The air molecules, primarily nitrogen and oxygen, are slowing down. In a warm summer room of about 25 degrees Celsius or 77 degrees Fahrenheit, those molecules are zipping around at approximately 500 meters per second. As the temperature drops, their kinetic energy decreases. This is a gradual, orderly reduction in motion. Within your own body, a parallel process is unfolding with clinical precision. Your hypothalamus, the small but powerful region of your brain that acts as a biological thermostat, has already begun to signal your core to release heat. To facilitate this, your body initiates distal vasodilation. This is the physiological process where the blood vessels in your hands and feet expand. By sending warmer blood to your extremities, your body uses them as natural radiators, transferring internal heat to the environment so that your core temperature can drop by the necessary 1 to 2 degrees Fahrenheit required for deep sleep. Consider the physics of the bed beneath you. If you are lying on cotton sheets, you are interacting with a material that has a specific thermal conductivity of about 0.04 watts per meter Kelvin. This low conductivity makes cotton an excellent regulator for a summer evening. It allows for the slow migration of heat away from your skin without causing a sudden chill. As your body releases energy, the air trapped between you and your blankets undergoes convective heat transfer. The warm air rises and slightly cooler, denser air moves in to take its place. This creates a microscopic weather system within your bedclothes, a gentle, rhythmic circulation of energy that mimics the larger movements of the atmosphere outside your door. Outside, the nocturnal boundary layer has fully matured. Because the ground has cooled faster than the air above it, a state of static stability has been achieved. In meteorology, this is measured by the Richardson number. When this number is high, turbulence is suppressed, and the air moves in smooth, laminar sheets. This is the ultimate stillness of a summer night. The wind dies down because the energy that drives the mixing of air, the sun's heat, has been removed. At this very moment, the atmosphere is like a layered silk ribbon, each band of air resting peacefully on the one below it. If a light breeze does stir, it is likely a katabatic wind, a density-driven flow where cool air from higher elevations or even the tops of trees slides downward, pulled by gravity, to pool in the low spots of the landscape. Deep within your brain, the pineal gland is responding to the lack of light by increasing the production of melatonin. This hormone is synthesized from serotonin through a two-step enzymatic process involving arylalkylamine N-acetyltransferase. As melatonin levels rise in your bloodstream, they bind to receptors in the suprachiasmatic nucleus, the body's master clock. This doesn't just make you sleepy, it coordinates a systemic power down of your metabolic processes. Your heart rate, which may have been 70 or 80 beats per minute during the day, begins to settle toward a resting rate of 60 or even 50. Your heart rate variability, or the tiny fluctuations in time between each beat, actually increases, which is a sign of your nervous system shifting from the sympathetic state of action to the parasympathetic state of rest and recovery. Picture the moisture in the air as it reaches its own turning point. As the temperature of the grass and the leaves drops toward the dew point, the air can no longer hold all of its water vapor. The relative humidity reaches 100%. At this exact threshold, water molecules undergo a phase change from gas to liquid, a process called nucleation. They gather on microscopic particles or the edges of leaves, forming tiny droplets of dew. This phase change is fascinating because it actually releases a small amount of latent heat, about 2,260 joules for every gram of water that condenses. This micro-release of energy prevents the temperature from dropping too rapidly, acting as a natural thermal buffer that keeps the summer night air from becoming truly cold. It is a self-regulating system that maintains the cozy, balmy environment you are currently sensing. What's happening now within your cells is a shift toward metabolic maintenance. While you rest, your glymphatic system, a recently discovered waste clearance pathway in the brain, becomes up to 10 times more active than it is during the day. The space between your brain cells increases by 60%, allowing cerebrospinal fluid to flow through and flush out metabolic debris, such as amyloid beta proteins that accumulated during your waking hours. This is not a wash in a metaphorical sense, but a literal hydraulic clearing of the cellular landscape. Your brain is tidying its house, organized by the same circadian rhythms that govern the blooming of the evening flowers and the cooling of the Earth's crust. Notice how the ambient noise level has decreased. This is partly due to human activity slowing down, but also because of the acoustic shadow created by the temperature inversion. The sound waves from distant traffic or far-off sounds are being refracted upward, away from the ground, leaving your immediate vicinity in a pocket of profound quiet. In this silence, the only remaining sounds are the low-frequency vibrations of the house or the steady, rhythmic sound of your own breathing. Your breath is its own meteorological event. As you inhale the cool, 22 degrees Celsius air and exhale it at 37 degrees, you are contributing your own small pulse of heat and moisture to the room, a rhythmic exchange that has sustained you since the moment you were born. As you move closer to the state of stage 1 NREM sleep, your brain waves begin to transition from the fast beta and alpha waves of wakefulness to the slower theta waves, which have a frequency of 4 to 7 Hz. During this time, you might experience hypnagogic sensations, fleeting images, or a sense of floating. This is a sign that your reticular activating system, the part of your brain responsible for arousal, is dampening its signals. The sensory gate of the thalamus is closing, meaning the sights, sounds, and even the lingering warmth of the room are being filtered out. You are retreating from the physical world into the internal landscape of the mind, a transition as inevitable and orderly as the rotation of the Earth away from the Sun. Scientists discovered that the optimal thermal environment for human sleep is around 18 degrees Celsius or 65 degrees Fahrenheit. As the night deepens and the room continues its slow, radiative cooling, you are moving toward this perfect equilibrium. The warmth of the summer evening has provided the comfort, and now the cooling of the night provides the catalyst for rest. You are suspended in the perfect middle ground, warmed by the memory of the day and invited into the stillness of the night. The Earth's albedo, the tilt of its axis, the pressure of the atmosphere, and the chemistry of your own blood have all conspired to bring you to this exact moment of readiness. Observe the steady rise and fall of your chest, a movement governed by the autonomic nervous system. Each breath is a commitment to the rhythm of the planet. Just as the seasons turn and the day yields to the night, your body knows exactly how to let go. The energy of the summer sun has been processed, stored, and now, in the quiet of the darkness, it is being used to fuel the quiet work of restoration. You are safe. You are part of an ancient, geological, and biological sequence that has never failed. The warmth is fading into the cool, and the cool is leading you into the deep. Repeat these thoughts silently as the world continues its slow, silent rotation. I am in harmony with the rhythm of the seasons. My body knows how to release the day and embrace the rest. The warmth of the evening is a blanket of safety. The coolness of the night is a pathway to peace. I am a part of the Earth's steady, breathing pulse. The stars are now at their zenith, and the summer triangle is high overhead, marking the deep middle of the night. The temperature has reached its stable nocturnal low, and the air is perfectly still. The work of the day is complete. The physics of the evening have fulfilled their purpose, delivering you from the heat of action into the sanctuary of stillness. The molecules of the air are quiet, the cells of your body are at peace, and the world is holding its breath in the velvet darkness. Good night.